In this example, we have to determine if the system is going to break loose. So the way I normally handle this is to assume that the system is not going to break loose, so it's a static system, and then we're going to start comparing forces around the system and find out whether or not the static friction force is maxed out or whether it's less than its maximum possible value. So if it turns out that we require a static friction force bigger than possible, then we know it breaks loose, and we have to change our strategy to one where the system is accelerating and we're using kinetic friction instead of static. So again, we're going to assume first that it doesn't break loose, and I'm going to do a force analysis. So looking at the hanging mass here, the weight is mg, that's 2 times 9.8, that's 19.6 newtons. The tension in the string, because I'm looking at a static system, must be equal to the weight pointing down. That's absolutely not true. These things are not equal if the system is accelerating, but as long as it's not, they must be equal. That means this tension is going to be the same everywhere in the string. It's going to be 19.6 newtons. Then I get into the standard analysis on a tilted coordinate system for this 5 kilogram mass. And that allows me to break the force of gravity into parallel and perpendicular components. Things are getting a little crowded, but I think it's manageable. And I have mg equals 5 times 9.8, which is 49 newtons pointing down. This angle is the same as this angle, which is 30 degrees. And I'm going to get a perpendicular component of gravity . Again, that's the projection of the weight vector onto the perpendicular axis. That's going to be mg cosine theta, or 49 cosine 30, or punching it in real quick, 49 cosine 30, it's 42.4 newtons. Then I look at the parallel component, and that's going to be an mg sine theta, or 49 sine theta, or sine 30. Sine 30 is 1/2, so this is 24.5 newtons. And then I've got a normal force pointing up. There's no other forces messing around with this perpendicular direction, and my mass is constrained to the surface of the ramp, so there better not be any acceleration happening perpendicular. N has got to be equal to 42.4 newtons to cancel out that perpendicular component of gravity. Okay, so let's take a step back and see what we figured out. This block is being pulled up the ramp with 19.6 newtons of force. It's being pulled down the ramp with 24.5 newtons of force. And so I have a net force pointing down the ramp. So this thing would just take off and start accelerating. However, we have a friction force available to us. So I'm going to put that in. And now I know which way it points. It must point up in order to keep this block locked in place. And so I could get a magnitude on that, but then I have to double check that it doesn't exceed the maximum possible. So my Fs, if I just write down an equation real quick, here I'll just work at the bottom. Let's call up the ramp positive. So I have T plus Fs must be equal to mg sine theta to keep this thing locked in place. Now we could be wrong and it could turn out that it breaks loose, but we'll hope that this pays off. And so Fs is going to be mg sine theta, that's 24.5, minus T, which was 19.6. And I get 4.9 newtons for that. It doesn't seem like a heck of a lot of friction, so I think we're going to be able to keep this. 4.9 newtons. And then I'm going to check. is Fs, assuming it doesn't break loose, is that greater than the maximum possible value? So let's compute the maximum possible static friction force. That's mu s times n. And that's 0.6 for mu s times the normal force, which was 42.4. So yeah, I think we're going to be fine. That's 25.4. So the maximum possible static friction force is 25.4 newtons. And since we only require 4.9 newtons to keep the block held in place, the system is not going to break loose. So since our required friction is less than or equal to the maximum possible, it's not going to break loose. So it won't break loose. Okay. Compute the tension in the string. We happen to have done that along the way. So there we go. So if at some point during the analysis you figured out that the static friction force required to hold this in place was larger than the largest possible value for the static friction force, you basically have to start all over, but you get to reuse a lot of the parts, a lot of the force decomposition and all that you've already done.